So we have made alcohols, we've made epoxides. We're going to make the epoxide in step 1 and use a second step to react it and make another functional group. Dihydroxylation, also known as diol formation. Diol, 2 alcohols, 2 OHs. So we install the first oxygen with the epoxide. We install the second oxygen by opening an epoxide. They're strained. They're actually fairly easy to react and open back up. Okay, so alkene becomes epoxide. So we're going to draw that first. Step 1. We're not going to concern ourselves with both the top and bottom attack, especially since this is a symmetric scenario, but we are going to just open it anyway. So we're going to look and see what's possible here, okay? So I'm just going to show one path. We'll do let it come from the top. But notice that this would have been the same if I had come from the bottom, right? So I could have had the OH, the epoxide from the top to the bottom. Now, every time I've covered a mechanism in lecture videos, I'm not going to be doing the mechanism every time, that same mechanism every time. We just would run out of time for it. So if that bothers you, this step 1, go back to the previous video and do the mechanism again, okay? But I'm going to take it for granted that we know an alkene becomes an epoxide with the addition of RCO3H. Step 2, I'm going to show you this mechanism that we can open an epoxide with base, basic water. So it doesn't have to be NaOH. It could be KOH, it could be other things, or just OH minus might be shown there. But that's the idea, is the hydroxide is going to be the base, and it will attack. And it can attack any of these carbons. So it can go here and open. Or it can go here and open. The important thing to note is that it's going to do an SN2 style backside attack. So if I do the red path, I'll write out the product here in red. Notice this carbon was unchanged. It gets to keep the O minus. So it gets to keep the oxygen that was originally there. See that? Open, so that one keeps it. The new OH ends up on that carbon. That's where it attacked. But because the wedge position was occupied, the hydroxide has to come in from a dashed position. So the new OH is dashed. Now let's do the blue product. It'd be the exact opposite, right? So we attacked from the back, the new OH goes there, that opened up, and the top carbon gets to keep the original O in the form of the O minus. Now we're in water, so we're not going to leave this as is. We're going to neutralize. So you can show that step, or sometimes, because like I said, we're doing more complicated mechanisms, the acid-base proton transfer might just say H+, and you acknowledge that you know what that means. But it doesn't hurt to write it out every now and then, too. You don't have to always skip it. So let's do that again here. Neutralize. So the main part of it was already accomplished in that first step. It's just this was neutralizing, because we're not going to isolate that anion. We're trying to isolate a diol, right? And let's take a moment to observe our diols. So notice they are 1, 2 diols. In other words, if I call one of them number 1, I get to number 2 before I have to stop numbering. So they have a 1-2 relationship. We have a 1-2. So that's the regiochemistry, 1-2 relationship. The stereochemistry is that they are anti. So regio is 1-2. Stereo is anti. Get anti-1,2 diol, anti-vicinal diols even. So I'm putting all these words here. Vicinal, anti-diol. And it could be done 2 ways. This is the mechanism for base conditions. If we present a base route, we will often give you an option for an acidic route. And that might feel like you're learning double, which you kind of are. At least there's some commonalities between them, but it's necessary because some things are base sensitive, so that's the time to use acid. Other things are acid sensitive, it's time to use base. You don't have to make a lot of those decisions quite yet, but you have to have these under your belt by the time when it's time to do that, okay? So let's show the acid mechanism. Step one's the same. I'll get us to that same epoxide that we're done with. Now we're going to open the epoxide. But when we have an acid, we don't attack it with a hydroxide. There's no hydroxide does not exist in acid. So knowing that we have acid, and remember this means H3O plus, we are going to draw that out because we are doing the mechanism with the whole thing. You are going to protonate that epoxide, oxygen. This makes it terribly strained now. It already wanted to open, now it wants to open even more because that would help neutralize it. And the water is going to do that job. It's going to be our nucleophile because we don't have hydroxide. Acid mechanisms are always longer because we have to neutralize and we use these nucleophiles that aren't ready to go. They get neutralized later. So just like above, we could do the red path to open, or we could have done the blue path, which is how we explain the formation of the two different possible enantiomers. Okay, so I'm going to draw out the red one. Let's do a red arrow. Okay, attack from below, water. The oxygen is what attacked and everything attached to it. It released, that carbon released its bond to the OH. That's ready to go. This time there's no negatives, right? So it's a good thing to compare. We just did a base mechanism, negatives were there, the dominant charge. The charges in an acid-driven mechanism is positives. Okay, here's the blue path. Here we go. So the dashed OH2, positively charged oxonium ion, wedged OH. Neutralize time. Now, if you feel like, yes, this is getting long, I'm just going to say minus H plus to neutralize. I will believe that you know what that means if you were getting the rest of that down. So if you took off that H and made that neutral, because you knew that's what you wanted to do here, I'd believe you. Okay, so another way to get an anti-diol, 1,2 diol. Without using a base. So these are your final products. Notice they're the same. You want to know both ways. Anti-stereoselectivity. Anti-1,2 diol. Using acid or base. All right. The question here that remains is, am I forced to be stuck with anti? What if I really, really, really wanted a syn diol? Don't worry, I got you. Osmium tetroxide or KMNO4 to the rescue. They will both give us a syn diol. Now, osmium tetroxide looks like this. And KMNO4 likewise uses manganese. And their mechanisms are not as clear-cut with arrow pushing. So what I'm only going to show you and ask you to kind of keep in mind and remember is the first step, because that explains the stereoselectivity It helps us get a syn. So in other words, we are going to see this when we're done. OH, a syn 1,2 diol. So you can at last get it, but in terms of mechanism, this is the only part that I'm going to ask you to kind of keep in mind because it helps explain the syn selectivity. So if we draw out one of these O4s, by the way, look at that oxidizing agent with all those oxygens. Not a surprise, right? We added 2 oxygens. All right. So if this approaches from the top, which it could also approach from the bottom, but I'm only going to show one because the other would be the same, just be redundant, and twice as long of a video for you to watch. So this actually makes a ring, even though it's part of a ring. It makes a second ring, like so. And see all those arrows at once? In order to make this ring intermediate, they have to be on the same face. And if this approached from the top, that would mean those electrons are going up toward that osmium tetroxide. Okay, so I'm going to connect that back to the osmium. These were untouched. Okay, so this was kind of the key intermediate here. I'm not going to show any additional mechanism. I just wanted you to see the syn nature. The syn is set in stone right here, syn oxygens. But through a lot of other detailed steps that you're not going to have to know, the second step is the workup. This is a reducing agent to remove the unnecessary pieces, the osmium and the remaining oxygens, to get us to the alcohol, the diol. It'll allow us to have our syn diol. Okay, both of them are 1,2. So anti 1,2 diol, syn 1,2 diol. Good oxidizing reagents there. Last big oxidation reaction. This is a student favorite. Not sure why. I think it's because there's something kind of rewarding about doing this. So here's our generic format. This is called ozonolysis, using ozone, O3. Okay, not O2, O3. Once again, heavy oxygen content. The second step is our reducing agent, which is DMS. Written out as dimethyl sulfide. Could be Me2S. It could be the whole Lewis structure, like that. So you should recognize all of those different ways of writing out DMS. Very common second step. Now, what we get here is our product. For the first time, we're going to be making ketones or aldehydes. So in other words, A, B, C, or D will equal R or H. And look at what happened. This is also called oxidative cleavage, cleaving the alkene bond and oxidizing in its path. Cleaves right there. So you can imagine separating that at that squiggly line and putting an oxygen on both sides, and voila, there you go. That's not the mechanism, but that's an easy way to kind of remember what's going on there. It's okay to kind of think of it that way because it's a complicated mechanism once again, and we go through some of it, but we're not going to go through the entire detail. So what you want to be able to understand is maybe just the first mechanistic step will get us to one of the intermediates called malozanide. So I'm going to redraw my alkene where I have a little more space. And I'm going to draw the Lewis structure of ozone. It has a plus and a minus next to each other because you can't have 3 bonds to oxygen without doing that. That helps make it more reactive. So if this wanted to make it a bond here, it would have to leave that behind, and then this would subsequently attack because that would be electron poor. And then we have, notice how we made a ring, a 5-membered ring. 3 of the members of the ring are oxygen. Quite a structure. It looks like a little cathedral or something. So this is an intermediate, has a name, malozanide. There's several more subsequent rearrangements this does. So, but I'm going to show you how the collapse of this can help explain how we cut that carbon-carbon bond. That's really the key kind of to understanding what happens here, but I don't think we have to do all the iterations. So this carbon-carbon bond, I'm going to call it A, B, A, B. We're going to watch that cleave or cut. Right there, it's broken. A and B aren't bonded anymore. That's as this ring collapses down to form the next intermediate. And voila, we form carbonyls in that step as well. So that helps explain it. It's not quite there because look at what one of them looks like. B is over here now. That's carbon B. And carbon A has some more mechanistic steps to go through before it's got that persistent extra oxygen hanging on. But as you can see, it's going to resemble the final product, because if we acknowledge that's really what we're doing, draw on your H if you need to. And we have that ketone, methyl ethyl ketone, plus this aldehyde, which was carbon A and B. Okay, so that's our final product. So I'm going to say more mechanistic steps, but we're not going to belabor them in this class. Kind of fun, right? I mean, yeah, the mechanism's a little funny at first. You should see the whole thing. You can look in your book and there'll be more of it. But I do like this step simply because it does illustrate carbonyl formation, carbon-carbon bond breaking. And then it kind of reiterates itself several times before it finally gets to the punchline here. But these are actually kind of fun. And one thing to watch out for is what kind of products you get. So here you can get 2 products. But what if you have a cyclic case? It's still connected somewhere else, right? So let's do a cyclic example. Cut right there. The way I like to do the cyclic examples is simply to, before I straighten it out, just put that oxygen in there where the pi bond used to be. And even draw your H there if you're worried about missing it. Then of course, if you're going to look at the solutions manual, because you're doing homework, it's not going to draw it all kinked up like that. It's going to rotate. So number your carbons to check it before you straighten it out. 1, 2, 3, 4, 5, 6. Then draw your appropriate number of carbons. I think I need one more. Number them. 1, 2, 3, 4, 5, 6. All rings changes in rings, whether they open or close. I always recommend numbering those carbons. So 2 has the ketone carbonyl. 6 has the aldehyde. That's probably how to look. And the H is not always drawn on the aldehyde. That's the final answer. So if you go from cyclic, you're going to have 1 product still with 2 carbonyls. Acyclic with 2 carbonyl bonds. But if you started with acyclic, you're going to have 2 separate carbonyls, right? Carbonyl containing compounds. Now, alkynes can also do ozonolysis, and we will revisit it again in the alkyne chapter, but since we've brought up alkynes now, ozonolysis now, sometimes it's easier to address it at the same time. So we're going to use water instead of DMS in our workup. But there are other options for workup which will give you different products, and other books will include more and some will include less. So I'm sticking to the one route for the sake of this class, but it's the same idea. Cleave down all of the pi bonds. It just gets extra oxidation. So instead of, so here's our, number those carbons, 1, 2, 3, 4, 5. So the first piece will have 3 carbons. The third carbon is where we get our carbonyl. All right, and then with water, that does some extra oxidizing to allow us to get to a carboxylic acid. Same with the other side. 4 and 5, so this is 1, 2, 3, 4 and 5. Carbon 4 is where we have our carbonyl, which is a carboxylic acid, and then we have our methyl, which is carbon 5. So let's write that out. We get 2 carboxylic acids. This is an internal alkyne does that. Internal means the alkyne is in the middle. There's R groups on each side. A terminal alkyne means that we have an H. It's at the end. So what happens when we cleave just one carbon, and we can oxidize both sides of it. So you can oxidize the sides that don't have R groups. We have the one single carbon that can oxidize the right side and the part that gets cut. It gets fully oxidized to CO2. So let's count our carbons. 1, 2, 3, 4.
Makes 1, 2, 3, 4 all together.
You're going to get your 3 carbon chain. 1, 2, 3. Carbon 3 gets the carboxylic acid functionality. 1, 2, 3. Carbon 4 becomes CO2. That can be mysterious because it's not always drawn. It's a gas, right? So your answer key might just show this, and you say, oh no, I lost a carbon. I must have had a terminal alkyne, right? So watch for changes in numbers of carbon.
Bring the crashes to the party, and you know me. Turn the O2 into the O3, dog. Without 40.